Okay, so welcome everybody. This is a master defense of Gabriel Laboy. We have several people present, and I want to welcome Mr. and Mrs. Laboy, who are the parents of Gabriel. This is a master defense, as I said. We have also people remote. The committee member are Dr. Swaminathan. I say Dr. Sai normally. Jack Marquez and myself. Gabriel, you have 30 minutes to present your work that you have been doing during the past 2 years. And then at the end of which the committee will have questions. Then the attendees, remote and present, can have questions for you. And then we ask you to leave the room, all of you. The committee will discuss and we will deliberate. So with that said, Gabriel, you have the stage.
All right, let's rock. Good morning, everybody. Thank you so much for coming out. Friends, families, collaborators, co-workers alike. Yes, I am who Dr. Taufer claims to be, Gabriel Laboy. Today, I'll be defending my thesis, advancing the GEOtiled framework for scalable high-resolution terrain parameter computation within the applied sciences.
Your head is cut off in the screen. Go ahead and just tilt it a little bit up. That's great. That's
okay,
perfect.
Wonderful. Okay, first and foremost, acknowledgements. I, of course, would like to thank my advisor, Dr. Taufer, for allowing me to do such wonderful research here at the GCL lab and also do this thesis. My committee members, Dr. Sai and Dr. Marquez, for grading me and taking the time here today to review my thesis content. Our collaborators from the University of Delaware, Dr. Vargas and Dr. Llamas, for their amazing, wonderful input on the domain science aspect of my work, and the many, many members, existing and former members of the GC lab, for all their helpful feedback on writing, critical thinking, and everything in between related to academia to put this work together. And of course, all the work here is generously funded by the National Science Foundation. As for published work, we are trying to get the word out there about the work in this thesis. So first and foremost, in tutorials, we have integrated the GEOtiled software within the National Science Data Fabric tutorial project, and which has been presented at numerous conferences, courses, and of course, the NSDF web seminar. As for conferences, tangentially related, I have presented work at AGU last year on a project related to mapping irrigation using machine learning. And we are trying to use the GEOtiled software to generate data as input parameters for that machine learning in that project. And of course, the work in this thesis has been published to submitted to HPDC as a poster presentation is currently under review. Finally, to kind of demonstrate GEOtiled's capabilities, we do plan to publish a very large data set to NASA for all terrain parameters it can do for the CONUS 10-meter region to help make data like this more accessible to scientists, since it may be difficult to curate data such as this. So first, let me go ahead and talk about what a terrain parameter is. Not too complicated, just simply when we say terrain parameters, we're referring to the physical characteristics of the Earth. Terrain, or the surface, so those can include things like the elevation, slope, incline, and position on the Earth, and things such as topographic wetness index, which use physical characteristics to sort of make a metric for how wet a region of land can be. And for how we use these, terrain parameters have various applications within the earth science, vital in certain studies. For example, with soil moisture, typically soil moisture collection, as it used to be, was you'd stick a sensor in the ground to collect information. This is very good, but is very time consuming and expensive and difficult to do with large regions. So we can use things like, and of course, there are stuff like satellites, which collect the soil moisture information at very low resolution, which of course kind of loses this granularity we have with physical. So we can use things like high resolution terrain parameters combined with machine learning to produce upscale sort of the resolution of this soil moisture information. As I mentioned before, the project from AGU, we can use things like terrain parameter features to make determinations about where irrigating cropland is located with terrain parameters as input features to the machine learning model. And of course, some big things, I know a lot of stuff is happening recently with forest fires. We can use information about characteristics of physical terrain to determine how fire propagates and where we should put in efforts to help mitigate the fire from spreading even more. Now, as for how we get these terrain parameters, all terrain parameters for this study are derived from what we call digital elevation models, exactly what it sounds like, digital representations of the elevation of the Earth. And we can get these from sources such as the United States Geological Survey, or USGS for short. And they have these DEMs available at resolutions as fine as 1 meter, and they collect this information with LiDAR from satellites, which is how they are able to do that. But and then we use what are called geographic information system libraries, or GIS for short, to compute these terrain parameters, as the GIS libraries have implemented published algorithms into software that are able to derive these sort of terrain parameters from digital elevation models. Now, about the digital elevation model data, we do see that there is a rise in the size of this data as we, A, increase the resolution of the data at, and B, increase the scope of the region of interest we are analyzing. So as you can see, going from Tennessee to CONUS and from 30 meter to 10 meter, we can see as big as a 200 times increase in the size of the input data for this digital elevation model from 2 to 400 gigabytes. So quite a lot of information to work with. And kind of tracking back to those GIS libraries, what's kind of out there to help produce these terrain parameters from these digital elevation models. So first up is the Geospatial Data Abstraction Library, GDAL for short. It's pretty compute efficient, or that just means it's relatively computes stuff very fast, but only computes a very limited number of terrain parameters, 3 of which we're interested in. And its data is specializing in data abstraction, so its predominant focus is more of computations such as resampling, reprojection, and of course does not offer any sort of utility to offer scalable computation as our data increases in size. On the other side, we have the System for Automated Geoscientific Analyses, or SAGA. This is a much more compute demanding library, or just runs slower compared to GDAL, but does implement hundreds of terrain parameter computation, since it is a library dedicated to implementing published algorithms that do these geoscientific analyses used from DEMs. And of course, also does not offer any sort of good feature to provide scalable computation as we get that increased data size either. So kind of the first steps to the scalable computation, the GC Lab has originally developed GEOtiled 1.0, designed to provide terrain parameter computation by leveraging concepts of data decomposition and parallel computation. Now, it does use functions from the GDAL library for its first iteration. So right now, we are encountering some limitations due to the limited number of terrain parameters from GDAL, meaning limited applicability in earth sciences, and some aspects we can improve to provide additional scalable performance by leveraging the same concepts that GEOtiled 1.0 already has. So for this thesis, we propose that we can expand a tool like GEOtiled 1.0 to generate a broader set of terrain parameters, and of course, continue to provide additional scalable performance so we can continue to see good execution time in producing terrain parameters for larger and larger input data sets as we increase the resolution and region of interest of these digital elevation models. So for our contributions, we will first extend GEOtiled 1.0 to GEOtiled 2.0 with the integration of functions from the SAGA library to increase the number of computable terrain parameters. We'll also optimize some components of the GEOtiled 2.0 framework to provide more scalable performance and also mitigate the cost of using compute demanding libraries such as SAGA. So first, before we go into the contributions, kind of GEOtiled nutshell 1.0. The overarching workflow is kind of divided into these 5 key steps here, which I'll explain each briefly. So of course, the first step is downloading the said digital elevation models. We get those from the USGS, and it'll give those a series of DEM files. And sort of in a pre-processing step, we will merge all these together and reproject into a different format of units, so that way it is compute compatible with the functions implemented by the GIS libraries. GEOtiled will then prop this pre-processed DEM into a series of tiles with buffer regions, and where the buffer is included as a means to preserve accuracy, which I'll explain later in this thesis. And then for all the tiles we produced from that propping stage, we will then concurrently compute our desired terrain parameters from each of those tiles, producing a series of terrain parameter tiles, or tiles. And for the final step, we want a single image, so we will take those terrain parameter tiles we produced and mosaic all those back into one single file as our final data. So now, on to our first contribution, the extension to GEOtiled 2.0 with the inclusion of SAGA functions. And this will take place in step 4, where the computation of terrain parameters happens within the GEOtiled framework. So what that looks like, what we've done is sort of plug it in puzzle piece. We now have in GEOtiled 2.0 our contribution, the ability for the user to select either GDAL or SAGA to compute terrain parameters. And of course, with the addition of SAGA, we have quintupled the number of terrain parameters computable by the GEOtiled framework from 3 to 15. And sort of what those looks like, as I mentioned in GEOtiled 1.0, the limited terrain parameter set while using GDAL only was on the slope aspect and hillshade. And now we have these wonderful 15 different terrain parameters you can generate and visualize with the GEOtiled framework, which helps increase the applicability to scientists and gives them access to more data to use for their studies. Now, we did mention that SAGA is more computationally expensive. So we, of course, want to make sure that we can leverage, of course, the concepts of data decomposition and current calculation to mitigate the cost of using SAGA and make it somewhat comparable to GDAL if possible. So to reiterate, when we refer to tiles, we're referring to a cropped file from the input DEM, so we produce a series of tiles. And the concept of data decomposition and current computation, right, as we decrease our tile size, or essentially increase the number of tiles we produce from the initial input DEM, and utilize concurrent computation, we can decrease our overall runtime to compute these terrain parameters. So before we get into our evaluation, we of course like to talk about a test infrastructure. So we use cloud infrastructure from Access, specifically Jetstream 2. This sort of infrastructure allows us to use multiple CPUs and actually leverage concurrent computation. And these test infrastructure we have here will be the same throughout all the tests we do through the rest of this thesis work. And sort of the configurations, talking about how we divvy up our tile sizes here. So for this test, we're going to do the region covering Tennessee at 30 meter resolution. And the way we divvy up our tile sizes is these are listed in kilometers, but each time we're essentially having the tile size or producing double the amount of tiles. So there's a direct correlation between tile size and the number of tiles we produce for the same region. So just understand that as this tile count increases, we leverage more parallelism to concurrently compute these tiles. Of course, we compare GDAL and SAGA as a means of comparison because we want to see it SAGA perform as well as GDAL. And also note that we go with slope in this case because slope is a shared terrain parameter between both the GDAL and SAGA libraries, providing a fair comparison. So the results, just a quick note here about what these graphs mean. We have our tile sizes from largest to smallest on the x-axis, execution time on the y-axis. On the left, we have results of computing with GDAL with GEOtiled 2.0. On the right, SAGA with GEOtiled 2.0. So kind of some key takeaways here is we see, of course, the decreasing time obvious due to the decrease in tile size, so decreased computation time. But the important takeaway here is that we have reduced the difference in time to compute the same parameter between libraries from GDAL to SAGA by about 96%, or what is around here, I believe around a 70 second difference down to a 3-second difference to compute the same parameter as long as you have small tiles. And it's important to note that we can only get this sort of reduction if we specify a small enough data decomposition size and we have the computational resources necessary to actually do this parallel computation. So those are keynotes to make sure that we can actually get this sort of performance. Now, with that wrapped up, we'd like to move on to the optimizations of the components of the GEOtiled 2.0 framework to make sure we can get that scalable performance we desire and also help further mitigate the cost of using demanding libraries like SAGA. Optimizations will focus on steps 3 through 5 of the GEOtiled framework, with our first optimization to the optimization to the crop function of the workflow. So first, before we get that started, I'd like to explain how tiles are created during the crop process. So what a user will typically do is specify a desired tile size, how big they want their tile to be from the input DEM, just as pixel size and column and rows, which will create a frame. This frame will create windows, and essentially this window will be passed over the input DEM. And for each window, we extract what we're interested in is essentially just corner coordinates. This is geospatial information. So when we say corner coordinates, they tend to be correlated to a latitude and longitude. But this information is represented as a 2-dimensional matrix. So all it really is just matrix indices, and that kind of creates our windows. With that window, we do 2 things. So one, we need to add this buffer border. And the reason why this buffer is important is with the computation of terrain parameters and the algorithms, for computation of a terrain parameter at a specific pixel, you need knowledge of the neighboring pixels. So by including this buffer, we ensure total accuracy of all the information within the window when we compute the terrain parameter. And so once that tile is cropped, what it's going to end up looking like, as you see here, shaded in the gray, is the main information from the window. And then kind of this white border here is the extra information added to each tile for that preservation of accuracy. So what is our optimization? Well, we essentially make this a concurrent process. So as I mentioned before, in the previous figure, these windows slide over one at a time. And for each window we crop one tile at a time. With the concurrent process, what we do instead is calculate all those windows first. So that is separate data. For each of those windows, we will then specify a series of concurrent instances in the multiprocessing pool to crop all those tiles from the input DEM using those series of windows to produce our tiles at the end. And I believe, yeah. So now the windows are stored as a list instead of getting a window at a time. And also we concurrently crop all those for the given list of windows to produce our tiles. Now, for analysis, of course, we would like to make sure that our optimization provides scalable performance, since we are using concurrency to help speed up this process. So for our test, we still work with the same input DEM of Tennessee at 30 meter resolution. And recall that as we, of course, decrease our tile size, we increase the number of tiles we produce for the same region, hence we leverage more concurrency. So we should see decreasing runtimes. So our results here with tile size on the bottom, largest to smallest, and on the y-axis, sequential in blue, and our parallel optimization in purple, we kind of get exactly what we were hoping for. Scaling computation, you can see in the purple as the tile size decreases, or we leverage more concurrency, we get decreasing runtimes up to an 8 times speed up for our 32 tile case over the sequential case. Now, for our second optimization, we will work on the mosaic function of the GEOtiled framework. So a bit about the previous mosaic procedure is it used averaging. So as I mentioned before, the buffer region, since it is copying information and the window is passed to make sure the borders are pretty lined up, what we end up having is we have essentially these overlapping or shared regions between tiles. So how it originally handled it is it would average these together. There was a scaling issue with this averaging method where if we continue to specify more and more tiles to merge together, there's more buffer regions that need to be handled. So we kind of had a scaling issue where we saw increasing runtime with this method. So for optimization, we propose a new method to mosaic, where we first crop off the buffer region. And of course, we can do this, as I mentioned, it's copy information. We're not losing any sort of geospatial information. We just choose to crop this buffer. And then we simply concatenate the tiles together. Additionally, as with the first optimization, we can also parallelize the crop of the buffer from in this mosaic optimization as well, so we can add some additional scalable performance to this optimization. So for analysis, of course, we want to make sure that we see faster scalable performance as we continue to decrease tile size or specify more parallelism. For our test, we do some similar stuff, same region, but this time, since the mosaic does take place after the computation of terrain parameters, we want to make sure that the terrain parameters being mosaic don't have substantial impact on the time to mosaic, because it is the same geospatial coverage, so there shouldn't be a major impact on the mosaic time. And then, of course, with the tile sizes, all the same as we've used previously for the crop optimization, since we're still working with Tennessee. As for results, the previous averaging method on the left and our new crop concatenation method on the right, the different bars represent the different terrain parameters highlighted here in this legend on the top right. So we have a few takeaways from this. First, we note that the slowest runtime for our crop concatenation optimization runs about 50% faster than the fastest runtime on the averaging optimization. So substantial performance improvement first, just using the crop concatenation method. We, of course, also note our scale performance. We are seeing a decrease in runtime due to leveraging more parallelism for the buffer cropping specifically. It's not a huge time savings because we only did parallelize one element of the 2 steps of the process. We do still get some, and we should see the performance, this scaling improve as we use larger input data sets. And finally, we also observed no major change in the time to mosaic based off terrain parameter, which is exactly what we were expecting. So this is expected behavior. Okay. Our third optimization will now encompass all of the 3 last steps of the GEOtiled framework. So kind of some background on what's been done so far, right? So this is kind of from the computation of the windows to the mosaic step, what kind of GEOtiled 2.0 is doing with our 2 previous optimizations. So remember with concurrency, we kind of specify these multi-processing pools for concurrent computation. So here we have optimization 1, or the concurrent computation of cropping, the concurrent computation of terrain parameters, the one that was already part of GEOtiled 1.0, and then the cropping of the buffer regions before the mosaic, which is part of our second optimization. So each of these multi-processing pools creates a little bit of overhead to spin up in order to do this concurrent computation. So what we can instead do is sort of unify these processes into a single multi-processing pool. And keep in mind that all the functions remain the same. We still have the crop, the compute, and the crop buffer. And we are able to do this due to, in some part, due to data locality. So these tiles still get created but during the computation, it's able to maintain knowledge of A, where that tile is located in memory, and B, oh, and yeah, it also knows when the previous function has completed, so that way it can immediately move on to the next function. So there, it also saves a little bit of time instead of having to wait for the stop of a finished multiprocessing pool and then spinning up the next one. Yes, and of course, the same output. Nothing changes between the input and output between these two procedures. So we, of course, would like to see some performance improvement from mitigating this multiprocessing pool, this overhead. And the test parameters here are identical to the mosaic process. Just do take into account, since we are measuring time from kind of the windows to the creation of these unbuffered tiles, the computation of terrain parameters is included here. So you'll see differences in time due to the computation of different terrain parameters, since they have different algorithmic intensity, but they should not impact the optimization improvement for the computation. Perfect. Okay, so results like the previous one on the left, we have the separated concurrency versus on the right, our optimization unified concurrency. What we generally see here is a very marginal improvement in time. Actually, in terms of percent reduction, it actually improves quite a lot as we get small and solid tile sizes. As you can see, for things like slope and aspect, we get around a 40% reduction in runtime, which is really good. Although, in terms of the absolute time, it is relatively smaller, since the cost of overhead is substantially smaller than the time to actually prop and compute the tiles themselves. Now, moving on. So what we're aiming for, the scalability test. So we want to make sure now that we have integrated the SAGA functions and that we've introduced all these optimizations, we want to make sure that GEOtiled 2.0 can now deliver scalable performance for computing terrain parameters as we move from small to large data sets. So for our test, we're going to move from Tennessee 30 meter to the CONUS 30 meter data set, about a 25 times increase in data size. And we'll essentially run tests on both of these to compare how well they scale. So the first test, you've seen it before, Tennessee 30 meter. Once again, we compute slope, since it's a parameter shared between GDAL and SAGA. And the same tile sizes before, where as we decrease tile size, we increase tile count, more parallelism. Results on the right here, purple is GDAL with GEOtiled 2.0, blue is SAGA with GEOtiled 2.0. Of course, we see the scaling performance we'd like, and we make two major observations. So we get around a 4 times speed up computing GEOtiled 2.0 with SAGA, going from the 2 to 32 tile case. And then also we see a 95% reduction in the difference in runtime between GDAL and SAGA, which kind of shows kind of the power here of data decomposition, concurrent computation. Now, for our large scale test, a few modifications. So we are encountering issues because of the way GDAL and SAGA are implemented, there's a lot of concurrent read and file writes. And so we modify the test here to account for sort of some memory inefficiencies. And what we do is simulate the computation of CONUS, is we compute the terrain parameter state by state, and then add all those runtimes together to simulate a run of CONUS instead. And so the main metric that changes here is we do tile counts per state. We dynamically determine evenly sized tiles to produce the desired number of tiles for each state to make sure we get consistent parallel computation using the same number of cores for each of the different tests. So results on the right here, exact same legend. We see some pretty good results, and we make two observations here in terms of the larger data set. So one, going from the 2 tile to the 32 tile count case, we go from about a 1.6 hour to 0.6 hour computation. So we save roughly an hour in computation time. That's roughly more than 50%. And also for the reduction, we reduce up to 86% in the time between using GDAL and SAGA, going from about a 30-minute to a 4-minute difference in computation. So also just really good numbers. So, summarizing the work of this thesis, right? We have extended GEOtiled 1.0 to 2.0 by introducing a richer set of computable terrain parameters for the GEOtiled framework, by implementing functions from the SAGA library. And we've also optimized multiple elements of the GEOtiled 2.0 framework to provide scalable performance through computational terrain parameters as our data increases in size. And our key takeaways from the work, just highlighting some results. So we can see that GEOtiled 2.0 can now compute 15 versus 3 terrain parameters of GEOtiled 1.0. GEOtiled 2.0 can reduce the time to compute the same terrain parameter using either library by nearly 96%. And of course, GEOtiled 2.0 can save up to an hour when we compute large data sets like CONUS 30 meter. And for our future work, we are interested in minimizing the file IO, and this may have to be through some more custom method because the way the SAGA and GDAL functions are designed is they are implemented to always read and write to files. Now, they do implement published algorithms, and these algorithms are, of course, all cited. So it may be that we can work with how Jean SAGA implemented and then modify it to not do that file IO, especially with unified concurrency, and we can take advantage of data locality to mitigate this. And of course, continue to integrate terrain parameters with the GeoTiled 2.0 framework. SAGA, like I mentioned, has hundreds of terrain parameters available for computation. And of course, we'd like to continue to update kind of that extension to GeoTiled, because if we can do more terrain parameters, we increase applicability and accessibility of these terrain parameters, especially as we increase, broaden the scope of GeoTiled to be able to have produce terrain parameters applicable to a lot of other studies. That's it.